In this section we explore the way that we can approximate irrational values, or perhaps rational but inconvenient values, using simple rational approximations. Recall that the tangent line is a blank 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 of a curve. I hope we all know the definition of a tangent line. It is a local, linear approximation. Super important that we know what that means. Local meaning in the area of the point of tangency. Linear obviously means like a line. Approximation means that it's very, very, very close to the curve. It is a good approximation of the curve. Remember, when you zoom in at the point of tangency, the tangent line and the curve appear to coincide. So we've got a picture of that here for the graph of the square root of x at x equals 4. We've got the graph of the curve. We've got a graph of that dotted tangent line. And we can see that in this local area, this point of tangency, you really can't see much of a difference between the tangent line and the curve. The farther away we get from that point of tangency, the more they deviate. But in that general area, they are very close to each other. So what we're going to do is we're going to use that tangent line to approximate the square root of 5, which is, of course, an irrational value. So we know that f of x equals x to the 1/2. We also know that f prime of x equals 1/2 x to the negative 1/2. So we can evaluate f of, well, at x equals 4, we're going to evaluate f of 4 is equal to 2. Square root of 4 is 2. And f prime of 4 is going to be 1/4. And you can see that on the graph. You can see that the slope of that tangent line is rise of 1, run of 1, 2, 3, 4. All right, so the equation of the tangent line, maybe I'll call it t of x equals the y value, 2, plus the slope times x minus the x value. All right, that's our point slope form that we kind of like to use. And that is the equation of this dotted line right here. This is t of x. And this is f of x. All right, so then we want to say, well, we know that t of x is approximately the same thing as f of x. It is a local linear approximation after all. So we know that f of x is approximately equal to t of x, at least when x is close to 4, the point of tangency. In other words, if 5 is considered close to 4, then f of 5 is approximately equal to t of 5. So the f of 5 is the square root of 5, and t of 5, well, we're just going to evaluate this by plugging in an x value of 5. So it's going to be 2 plus 1/4 times 5 minus 4, or 1/4 times 1, or 1/4. And that's going to be 2 1/4, or 2.25. So we find that the irrational value of the square root of 5 can be approximated by the very rational value, 2.25. I'm not sure if numbers can be more rational than other numbers. Either you're rational or you're not. But anyway, how good an approximation is that? Well, let's take a look. I mean, graphically, we can just kind of look at this, and we can see that at x equals 5, we can kind of go up to find that this point right here on the curve is the point 5 comma square root of 5. And this point right here on the line is 5 comma 2.25. Or if you prefer, you can call it 9/4. I don't care. And look at how close those 2 points are. You really can't see much of a difference between them. If you look very closely, you can see that perhaps the line is the 2.25 is just a bit of an overestimation. But this is a very quick and easy calculation that we can get to get a pretty decent approximation for the square root of 5. Now I encourage you to pull out your calculator, type in the square root of 5, see what that is as a decimal, and see how that compares to 2.25. And hopefully your calculator will verify all the stuff that we already suspect is true. So if we look at the graph, we can definitely see that that tangent line is always above the curve. And because of that, the concavity determines whether we're talking about an overestimate or an underestimate. So we can see that that the square root of x is a concave down curve. And if we can't see that, then we can look at the second derivative. We know that f double prime of x is equal to negative 1/4 times x raised to the 3/2. And for all positive values of x, which is the only type of, negative, the only type of x value we have in this domain is non-negative, x raised to the negative 3/2 is going to be positive. And when we take that positive number times negative 1/4, we'll get a negative value. So we are definitely concave down at x equals 4, the point of tangency, which means that our curve curves down away from the tangent line, which means that our approximation must be an overestimate of the actual value, right? And you probably found in your calculator that the square root of 5 was about 2.236 compared to 2.25. 2.236 is awfully close to 2.25, but 2.25 is an overestimate. So, so that's how we can kind of quickly use the concavity of the graph to determine whether our estimation is too big or too small. All right, so the reason we're picking x equals 4, well, two reasons, right? One is I told you to. Right here it says use the equation at x equals 4. But why did I pick that? Why did I pick x equals 4 to approximate this square root of 5? Well, there are two reasons. When we're taking the square root of 4, well, that's not something we need a calculator for. That's not something that's going to give us a messy answer. And second, 4 is close to 5, the value that we were asked to approximate the function at. So we could have drawn a tangent line maybe over here at 1, 1, but you can imagine that as we graph this tangent line, it's going to be way too high when we get over to x equals 5, because the local part of that is not really satisfied very well. So keeping that tangent line, that point of tangency, to be as close to the point that we're interested in as possible is really going to help get our approximations as good as possible. Okay, so when we talk about these differentials, and that's the change, the difference in the variables. One notation that we might see is delta x or dx. So I want you to kind of think about this as, again, the original equation is y equals x to the 1/2, and if we use Leibniz's notation here and we do dy dx equals 1/2 x to the negative 1/2, we can then say, oh, the instantaneous change in y, in other words dy, is equal to the derivative of our function times the instantaneous change in x. We call it dx. So what's the difference between dx and delta x? Remember that delta means the change between 2 points, and the differential, that's after we've applied the limit. So that would be the instantaneous rate of change, or the infinitesimal change in a particular value. So we can't really measure how big dx is, but we can measure how big delta x is, because we're talking about an interval value here. So so really what we did here in this last example is we were given an x value of 5, which was 1 bigger than 4. So we actually said, well, that means the delta x, or delta y, excuse me, is equal to 1/2 times our point of tangency value times our, whoops, I'm jumping ahead of myself, I'm sorry. I just wanted to start by talking about not the instantaneous change, but the, I guess maybe average rate of change. Here we go, that's what I meant. So this is following the curve, and this is following the tangent line. Okay, so our slope, our change in y divided by our change in x, if our change in x is 1, then our change in y at x equals 4 equals 1/4. 1/2 times 1/2 is 1/4. So our old y value of 4 changed by 1/4. It went up by 1/4 because it's a positive 1/4. It went up to, our y value of 2, f of 4 equals 2. Our original y value of 2 changed by 1/4. So our new y value is 2 plus 1/4, or 2.25.